Today we are talking about error bounds in power series. So, before we go to the notes page that is in your packet, I have this handwritten sheet that I put together a couple of years ago that I want to share with you. So, error in series. There are two types. There's the alternating series error bound that we already learned. If the terms are alternating in sign and decreasing in magnitude to 0, then the error bound is the magnitude of the first unused term. That has not changed. It's there and it will stay there. This is the more commonly seen one in FRQs on the AP exam. Okay? Now, what if the terms are not alternating in sign and decreasing in magnitude to 0? If they are not, then you apply the Lagrange error bound. And I like to think of the Lagrange error bound as the error bound is almost the magnitude of the first unused term. Almost. The difference is, the big difference is that you don't just use the next term. It is almost that term, and each term is in the form of a Taylor series term. Okay? Which means that in a power series, every term has this form, every term. So if you're using Lagrange, your error bound is in this form. It's in this form, almost. Okay? Almost. Instead of the nth derivative, we use the maximum nth derivative that can be on the interval from our center to the x value that they give us, that we're approximating. Okay? So I know that that's confusing. We're going to do some examples, but that is what Lagrange error bound is. All right? Always in this form, except it's the maximum nth derivative from x to c, from x to the center. It sounded like I said from x to c. It's from x to the center. Okay? All right? So remember that the derivative, the factorial, and the power are all the n value in your first unused term. So if you use up to the fifth degree term, then the sixth degree will be your error bound term. Okay? All right, another thing to remember, and this is crucial to remember, you will have numbers in for everything here. You will have no x's left, no c's, no n's, nothing. You'll have nothing left, okay? Only numbers. All numbers in Lagrange error bound. All numbers in the alternating series error bound as well, for that matter. Okay, so on this sheet, this is great information, but it's very wordy, and it has tended in the past to confuse some of my students, all right? I do have on there a little picture of Lagrange, for whom this theorem is named after, okay? Or for whom this theorem is named, all right? So there's a little blurb on Lagrange, okay? Here's our Lagrange error bound, okay? Let's get to some examples. I like to get to the examples as soon as I can here because I want you to see that it's not as awful as it sounds at first. Okay, first of all, no. The alternating series error bound is still in play. And if your terms are alternating in sign and decreasing in magnitude to 0, then that is the error you use. Do not use Lagrange if that is the case. Okay? All right, let's say that we are given f, a function, and it has derivatives for all orders, for all real numbers x, and f of 2 is 6, f prime of 2 is 4, f double prime of 2 is -7, and f triple prime of 2 is 8. I don't have to read the rest of the question to know that I'm going to be centered at 2. I already know that. Okay? So I already know all of my terms will have an x minus 2 in it. Let's write the third degree Taylor polynomial for f about, surprise, surprise, x is equal to 2. And then we're going to use it to approximate f of 2.3. So first things first, I do what they say to do. Write the third degree Taylor polynomial for f about 2. The first term in the Taylor polynomial, so I am using, by the way, I am using my format for Taylor series. That says, I don't know why I put an S, that says f at c is my constant term. Then I go to f prime of c over 1 factorial times x minus c to the first power. Then I go to f double prime of c over 2 factorial times x minus c to the second power. The derivative, the factorial, and the power always match. Always match. If you're not matching those, you're doing it wrong. Okay? F triple prime of c over 3 factorial times x minus c cubed. They are asking me to write a third degree Taylor polynomial. This is a third degree term, so my third degree Taylor polynomial will start at f of c and finish at this term. Okay? So let's plug in what we know. At x at c is equal to 2, I start with f of 2, and f of 2 is 6. Then I go to f prime of 2. F prime of 2 is 4 over 1 factorial times x minus 2 to the first power, plus f double prime of c is negative 7 over 2 factorial times x minus 2 to the second power, plus f triple prime of 2 is 8, divide by 3 factorial times x minus 2 to the third power. I kind of sit back a little bit and I look to make sure everything looks fine. I have a constant, 1, 2, 3, factorials look good, the derivatives look good, everything looks good. There you go. There's my third degree Taylor polynomial for f about 2. If you want to clean up this fraction, clean up the fraction. If you don't want to, don't. It doesn't matter. This is an FRQ. We're going to approximate f of 2.3 now. So this is our approximation for f. So f of x is equal to, do you see these x's? This is f of x. It's a function of x. Okay? A little messy, I don't care. It's a function of x. We want f of 2.3. Where are we going to put the 2.3? We're going to put the 2.3 in for x. So wherever we have an x, we're going to write 2.3. I'm just carefully going through, replacing every x with 2.3. When I'm done, I sit back a little bit and make sure I did it correctly. It looks good to me, so I think I'm okay. Alright, I have done what they have asked me to do. Let's go to part B. The fourth derivative. The fourth derivative of f satisfies this inequality. Read what this says. It says that the magnitude of the fourth derivative of f is less than or equal to 9, which means that the maximum the fourth derivative can be is 9 in the interval from 2 to 2.3, from our center to the x value that they gave me to approximate in part A. Right? So the fourth derivative, my polynomial went up to the third derivative. The maximum fourth derivative in this interval is 9. Use the Lagrange error bound on the approximation of f of 2.3, that's this, found in part A, to find an interval in which the exact value of f of 2.3 must lie. Okay? All right. Well, the error bound is, okay, here it comes, Lagrange error bound. What is the form? It's the form of a Taylor term. Derivative, factorial, power, all match. The derivative. This is the maximum fourth derivative, which they gave me. This is the easiest kind because they just gave me it. The maximum fourth derivative is 9 divided by 4 factorial times. Okay, I want to put an x minus 2 here. I want to do that to the 4th power. I want to put an x minus 2 to the 4th, but I'm not going to put an x. I'm going to put the 2.3 that they gave me. So 2.3. Because in an error bound you have no variables. It's all numbers. No x's, no c's, no n's. Just numbers. Okay? So this is the error bound. That's the error bound. Okay? I want to write an interval in which the actual value of f of 2.3 must lie. This is my approximation using just those terms. I'm going to call that A. I'm calling it A for approximation. Okay? I'm going to call this E, capital E for error bound. Okay? The actual f of 2.3. So, think of it this way. We know it's almost A. It might be a little higher or a little lower than A, than our approximation. It's somewhere, there's an interval. It's either a little higher or a little lower than A. This is how much higher or lower it can be. So this is between A minus E and A plus E. This is a little number. It's a tiny number. Well, it's a little number, okay? So the actual value is between, it's almost the approximation, give or take that error. Okay? That's how I like to think of it. All right, the function g. G is now defined by f prime of x. Write the second degree Taylor polynomial for g of x centered at 2. This is an easy one because here's f. We want f prime. And I know how to take a derivative. Here's f. We want f prime. Easy peasy. What's the derivative of 6? 0. So the first term is 0. What's the derivative of this piece? Little chain rule here. Little chain rule. 1 times the coefficient is just the coefficient. And I know 1 factorial is 1. I'm just making a point by just not simplifying that, okay? You don't have to simplify that. Times x minus 2 to the 0 times x minus 2 to the 0. Anything to the 0 is 1, but this is a safe stop spot. I can just leave it like that. I could also have said for the derivative of 6, I could have put 0 right there. Of course, we don't have to, but I could have, okay? All right, the derivative of this. 2 times the coefficient. 2 times negative 7 is negative 14 over 2 factorial times x minus 2 to the first power. Little derivative. The derivative of the inside would just be a 1, so that's I don't have to worry about the derivative of the inside of these. Okay, this one. 3 times the coefficient. So 3 times 8 is 24 over 3 factorial times x minus 2 squared. And we're done. We took the derivative. This is the second degree. This is the second degree Taylor polynomial for the derivative of f, centered at 2. Okay. Love these problems. I think they're so interesting. Okay. Number 2, little multiple choice question. The function f has derivatives of all orders for all real numbers, and it is known that the maximum fourth derivative of f is 7/5. This is the maximum fourth derivative is 7/5. And the maximum fifth derivative is 3/4. Okay? For x between 0 and 2. Okay. Let p sub 4 be the fourth degree Taylor polynomial for f about x equals 0. The Taylor series for f about x equals 0 converges at x equals 2. Of the following, which is the smallest value of k for which the Lagrange error bound guarantees that the error is less than or equal to k? So k is the error bound. Okay? So essentially, they are saying, what is the Lagrange error bound? That's what they're saying. Okay? We are using the fourth degree. Remember, this means the fourth degree Taylor polynomial. The fourth degree, which means that it goes up to the fourth degree. Okay? Fourth degree goes up to fourth degree. So k, the Lagrange error bound, will have the fifth degree in it, right? It'll be the maximum fifth degree, the maximum fifth derivative times x minus c to the fifth power divided by 5 factorial, all the fives, all over the place. So I'm going to be using this 3/4 because that is the maximum fifth derivative, 3/4, divided by 5 factorial times, I want to say x minus 2, not 2, I don't want to say 2, x minus the center. The center is 0. I want to say x minus 0 to the fifth, but it's not an x. It's never an x, all right? It's always a number. So let's put the number. What number are we using there? I'm about to lose charge here on my phone. Let me find my cable. Where's my cable? Good grief. There it is. Okay, sorry. Okay, we're back in action. Okay, I want to put x here, but it's never an x. It's always the value that they're using. What value of x are they approximating? They are approximating 2. So 2 goes here. That is the error bound. That is k. I just have to clean it up to make it match one of these, right? Well, I see something here. Of the choices, I'm looking at the choices, I see a 7/5, a 7/5, a 3/4, and a 3/4, I did not use the 7/5, I used the 3/4, so I know it's not one of these. It's one of these, right? Which one of those is it? It's the one with the 5 factorial in it, right? It's 2 to the 5th over 5 factorial times 3/4. It's B. I copied that right from AP Classroom, this problem. Okay, let's do another one. Last page. Oh my goodness, last page of the last day of new notes of the year, you guys. Holy moly. Oh, sad, sad, sad. I know. You have to blow your nose, wipe your tears, and then let's continue. Alrighty. Look what they gave us here. Look at this table. Never had a table that looks like this. The maximum second derivative of f on the interval from 1 to 1.2 is 5. The maximum third derivative of f on the interval 1 to 1.2 is 10. The maximum fourth derivative is 20. The maximum fifth derivative is 40. Okay. I have a feeling we're going to need to choose which one to use, right? Let p of x be the third degree Taylor polynomial. Let p of x be the third degree Taylor polynomial for f about 1, which is one of our boundaries in our intervals there. Okay? That's our C. That's our C value, right? Information about the maximum of the absolute value of selected derivatives of f. This came right from AP Classroom, you guys. Over the interval 1 to 1.2 is shown in the table above. Of the following, which is the smallest value of k for which the Lagrange error bound guarantees that this expression is less than or equal to k? This is another way to say error. So k is, once again, the Lagrange error bound. Okay? P is the third degree Taylor polynomial. This is the third degree Taylor polynomial. So therefore k will be of the form of the fourth degree Taylor term. The fourth degree. 4's all over the place. Okay? So we need to go to the maximum fourth derivative. We're going to ignore the second, the third, and the fifth. The maximum fourth derivative is 20. We divide by 4 factorial. We multiply by something to the fourth power. X minus c to the fourth power. Okay, but I'm not going to write x, and I'm not going to write c. I'm going to say what those are. C was 1. X is 1.2. Now I just need to clean this up to get one of these, right? So cleanup time. 20 divided by 24 times 0.2 to the fourth power. I would way prefer to deal with a fraction to a fourth power. So 0.2 is 1/5, right? 2/10, 1/5. So this is 20 over 24 times 1/5 to the fourth power, right? Okay. Let's see, there's a 4 in both of these, so that reduces to 5 over 6 times 1/5 to the fourth power. Okay, 5 and one of these 5s, so now that's just a 3, right? So this is 1 over 6 times 5 cubed is 125. 6 times 125 is 3, 12, 15 plus 750. I think it's 750. Hope it's 750. It's one of my choices, so there you go. D. Alrighty? Number 4. Oh, I forgot my drink. It's downstairs. Okay, that's all right. My throat is getting a little dry. I've taught all day today, and now I came home to make a video for you guys. Okay. The function f has derivatives of all orders for all real numbers. And f of the, what does this say right here? It says that the 7th derivative of f is this function. If the 6th degree Taylor polynomial centered at 1 is used to approximate f on the interval from 0.5, that's a half, from 1/2 to 1, 1 is the center. What is the Lagrange error bound for the maximum error bound on the interval from 0.5 to 1? Okay, so of all the approximations from 0.5 to 1, which is the highest? Okay, which is the highest? So, since we're using the 6th degree Taylor for the approximation, the maximum error will have the 7th degree derivative in it, right? One, that almost the next one. Okay, so I need to consider what is the maximum error. What is the maximum that this thing can be on this interval? On this interval, what is the maximum? So let's think about that. My 7th derivative is e to the sine x. I want to know what's the biggest that this thing can be on this interval. Well, I know that e to a power, the graph of e to the x is always increasing, right? Always increasing. Is sine always increasing on this interval? Is sine always increasing on this interval? 0.5 and 1, where is that? It's in radians. I know it's in radians. 0.5 a half of a radian. Well, think about that, you guys. This is pi radians. That's pi right there, which is 3.14159 blah blah blah, right? 3.14. Where is 1 then? If this is a little over 3, where is 1? 1 is in the first quadrant, right? Therefore, a half is also in the first quadrant. Yeah? Sine in the first quadrant, the graph of sine in the from 0 to pi over 2 is always increasing, which means that the biggest sine can be is when x is 1, right? The biggest sine can be is when x is 1. So the max here will be when x is 1. So our derivative will have e to the sine of 1 in it, divided by 7 factorial times something minus c to the first, not the first power, to the 7th power, right? C here, what was our center value? Our center value was also, our center value was 1. Okay, that was our center value. And on the interval, we want the maximum, we want the biggest number possible. The biggest number possible. On this interval, what will give this the biggest number possible? Not a 1. If I put a 1 in here, it'll be a 0. And the answer choices kind of give it away. It should be a 0.5. Okay, that's what it should be. And keep in mind that this is absolute value. It's always absolute value. I'm looking at their choices, and they all have a positive 1/2, and in my form it's going to be a negative 1/2, but the absolute value is going to turn that into a positive. Okay? So which one is the correct answer? It looks like this one here, A. Tricky one. That was a tricky one. That's how you would came straight from AP Classroom, guys. Straight from there. All these on this page, well, these multiple choices did. Okay? All right. Next up, number 5. The Taylor series for a function f about x equals 2, that's our c value, is given by this. This is the Taylor series. And converges to f between 0 and 4. That's our interval of convergence. If the third degree Taylor polynomial about x equals 2 is used to approximate f of 9/4, what is the alternating series error bound? Oh, alternating series error bound. Well, the alternating series error bound is not Lagrange error bound. Alternating series bound is just the next term. That's what it is. It's the absolute value of the next term. So, the third degree Taylor is the approximation. So, when n is 3, I will be at my third degree term, right? Well, that means that the error bound will be the next one. The error bound is when n equals 4 then. All we have to do is plug in 4, take the absolute value. Okay? And we're putting 9/4 in for x. No x's left when we write the error bound. Okay? So I'm going to ignore the -1 because it doesn't matter. Error bound is absolute values. So I'm ignoring that. The error bound is never negative, always positive. So 3 times 4 is 12, plus 1 is 13, divided by 2 to the 4th, times 9/4 minus 2 to the 4th. I just simply put 4 in. Okay, let's see, which one is this? Which one is this? Which one is this? Okay, I'm going to have to do a little work here, but I don't have to do a whole lot. I'm thinking it's probably this one because I see the 13 over 16 here. That is 13 over 16. 9/4 minus 2 is 1/4. And that puts the 4 to the 4th on the bottom here. So yes, the answer is C. Oh, hang on. Did I not do that right? Hang on. I got a different answer. Oh, I just wrote the wrong answer. I wrote on my answer key here, I put a D, but I did the right work. I just circled the wrong answer. It's C. Okay, next one. This one came from an FRQ on an old AP exam. F has derivatives of all orders. The third degree Taylor polynomial for f about x equals 3, that's our center. If it says about x equals 3, that means C is 3, is used to approximate f of 2.5, that's what we will put in for x with our error. And a third degree Taylor was used in the approximation. Okay? Which means the error will be the 4th degree term. Yes? 4th degree. A partial graph of the 4th derivative of f is shown on the right. This is the this is a graph of f of the 4th derivative. Okay? It is known that the graph has a horizontal tangent line at 3.53. That means that this is when x is 3.5. For a second, this looks like a -3. That it's not a -3. That's just the line. That's just the grid continuing. Okay, it's not a negative there. I'm like, what's going on over there? Okay, all right. And the points 2.52, 2.52, and 3, 2.8, 3, 2.8. So this is y equals 2.8. Are on the graph. Use the Lagrange error bound to show that the error in the approximation is less than 1/128. Okay, so Lagrange error bound, maximum derivative. We want the maximum derivative, the maximum fourth derivative on the interval. What interval is it that we want the maximum derivative out of? Remember, it always has c in it, and it has your x value in it. So we want it from 2.5 to 3. 2.5 to 3 is the only place we care about. 2.5 to 3. Oh, I went too far. 2.5 to 3. This right here. That's what is the maximum. This is the graph of the fourth derivative. What is the maximum on this one, on this interval? The maximum on this interval is right there. That was our weird one, our 2.8. That is 2.8. So the maximum is 2.8. That's the maximum fourth derivative on that interval. Divide by 4 factorial times x minus c to the fourth power, but I don't put x and I don't write c. I need to put the x value that I'm using. I'm using 2.5 and my c was 3. Oops, c was 3. Been a long day, guys, sorry. Okay, alrighty. So, alright, and they say that they want me to show that that's less than 1/128, less than 1/128, and I am done. That's it. All you got to do. Okay? If you're afraid that this is going to be negative, it's to a fourth power, so I know it's not going to be negative, but if you're afraid, just slap some absolute values around there and you're good. Okay? Always positive. Error bounds are always positive. Okay. That is it for Lagrange error bounds, which means that is it for new material of this school year. Craziness. Craziness. Okay. You guys go try some on your homework. In fact, try all of them on your homework. Good night.